this episode, we'll take the mystery out of boot configuration by treating it like a set of instructions that shape how Linux starts, what it looks for, and what choices it makes before you ever reach a login screen. Boot problems can feel random because the machine fails early, sometimes without a friendly message, but most failures trace back to a small number of misaligned expectations. Those expectations are written down in boot configuration and in kernel parameters, which are simply values passed into the kernel at startup so it knows what to do and how to do it. When a system boots normally, you rarely think about these settings, but when something changes, the same settings become the difference between a clean boot, an emergency environment, or a complete stop. The goal here is to help you understand what these settings control at a high level, why small changes can have big consequences, and how the exam expects you to reason about them without turning the topic into a command-typing exercise. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A good starting point is recognizing that boot configuration is not one file in one place that always looks the same, because different systems and different designs store their boot instructions differently. What stays consistent is the idea that a bootloader needs a recipe, which kernel to load, where supporting files are, and what parameters to pass when the kernel starts. A common bootloader in Linux environments is Grand Unified Bootloader, GRUB. And even if a specific system uses a different approach, the exam mindset stays similar because the bootloader's job is to choose and launch. The configuration attached to the bootloader is essentially a menu of possibilities, even if you only ever see one default option. When you change boot configuration, you are changing the recipe the system follows at its most fragile moment, which is why mistakes can feel dramatic. For exam questions, the key is to treat boot configuration as the place where intent is declared, like which kernel should run and what the kernel should assume about the system. Kernel parameters are the next piece of the story, and beginners often think of them as obscure magic words. But a parameter is simply a named setting the kernel reads during startup. You can imagine the kernel as arriving at a blank stage and being handed a note that says where the props are, how bright the lights should be, and whether it should start in rehearsal mode or full performance mode. Some parameters tell the kernel where to find the root file system, which is the base of everything that will be mounted and used later. Other parameters adjust hardware behavior, control logging verbosity, or change how the system reacts when something is missing. Parameters matter because the kernel must make decisions immediately, and it cannot ask you questions the way a normal program can. If the parameter tells it to look for something that does not exist, or to use a driver or method that does not match reality, the boot process can stall. The exam tends to test whether you understand that parameters shape early assumptions, so a wrong assumption can break boot even if the underlying disk and files are fine. One of the most important consequences of boot configuration is that it defines what the system believes is authoritative at startup, which is why a correct system can become unbootable after a seemingly small change. If you point the bootloader to the wrong kernel image, the system may load something that cannot run on that hardware or cannot work with the installed modules. If you pass a root location that is outdated, the kernel may search for a file system that is not there, even though the correct file system exists under a different identifier. If you choose a configuration that expects a different storage layout, the early boot environment may not be able to assemble the disks in the way the real system needs. From the learner perspective, the big idea is that the boot chain is strict about order, so the wrong setting at the beginning can prevent later self-correction. This is also why boot configuration changes should be minimal and deliberate, because early boot does not offer many safety nets. Exam questions often hint at this by describing a system that worked until a change, and your task is to connect the change to the earliest assumption it would affect. To reason about why things break, it helps to separate changes that affect selection from changes that affect interpretation. Selection changes are about what gets loaded, such as which kernel version is chosen or which entry is used as default. Interpretation changes are about how the kernel behaves once it is loaded, such as what it considers the root file system or how it handles device discovery timing. Selection problems can show up as a sudden failure after a kernel update, where the old option might still exist but is no longer the default. Interpretation problems can show up as the kernel starting but then failing to mount the root file system or failing to reach normal user space. The exam likes this distinction because it gives you a clean way to eliminate wrong answers. If the symptom is that the system never even starts the kernel, selection is suspect, while if the symptom is that the kernel starts but cannot proceed, interpretation is suspect. This is not about memorizing a long parameter list, but about understanding what category a parameter belongs to and what kind of failure it would produce. Once you train that lens, boot questions feel less like guessing and more like placing a clue on a timeline. A very common theme in boot failures involves how the system identifies storage, because storage identifiers are both necessary and easy to mishandle. Devices can be referred to by names that look simple, but those names can change depending on discovery order, hardware, or configuration. The boot process often prefers more stable identifiers, like a file system label or a unique identifier, because those remain consistent even if device ordering changes. When boot configuration uses an unstable identifier, a system might boot one day and fail the next after a hardware change, a firmware update, or even a different timing pattern during startup. The reason this breaks is that early boot needs to find the correct root file system quickly, and if it looks in the wrong place, it cannot just continue and fix it later. For the exam, you should recognize that stable identification is a reliability strategy, and boot configuration is where that strategy is applied. If a question describes intermittent boot issues after hardware changes, suspect identification and assumptions before suspecting random corruption. Kernel parameters can also influence how much information you see during boot, which matters because visibility changes how you interpret what is wrong. A system can appear to freeze when it is actually waiting for something, or it can appear to fail silently when it is failing loudly but not displaying the messages you expect. Some parameters adjust whether boot messages are shown, how verbose they are, and whether a graphical display hides them behind a splash. This matters because a hidden message can make a simple problem feel mysterious, and exam questions may include clues like seeing or not seeing certain kinds of output. The mental model is that the system always has a narrative of what it is doing, but your view into that narrative can be filtered. When you think in that way, you avoid the beginner trap of assuming that a lack of messages means a lack of activity. It also reinforces a broader exam skill. Sometimes the best answer is the one that increases clarity and reduces ambiguity, rather than the one that makes the biggest change. Another way kernel parameters break systems is by forcing the kernel into a mode that does not match the environment the machine is actually in. Some parameters are designed for troubleshooting or special contexts, like telling the kernel to use a simpler driver approach or to avoid certain hardware features. That can be helpful if you are diagnosing a problem, but harmful if it becomes the default and the system relies on the disabled feature. A classic example pattern is when a parameter is used to get a system to boot once, but then it is left in place and causes reduced functionality or instability later. This is a helpful exam lesson because it teaches you to treat troubleshooting settings as temporary and context-driven, not as permanent solutions. The exam often rewards the safest long-term choice, which usually means aligning the boot recipe with the intended stable configuration. If a question describes a system that boots only with special settings, the deeper issue is likely compatibility or driver availability, not that the special setting is the ideal permanent state. Good reasoning separates workaround from root cause. Boot configuration also interacts with the early temporary environment that prepares the system for normal operation, and this is where the terms initial RAM disk and initial RAM file system become relevant. On the first mention only, those are initial RAM disk, initRD, and initial RAM file system, init or AMFS. And the important part is that they represent a small early user space that helps the kernel reach the real root file system. The bootloader may specify which of these early images to load along with the kernel, and the pairing matters because the early image may contain drivers or scripts needed for the particular system. If the kernel version and the early image are mismatched, the kernel might start but fail to load needed drivers, or it might not be able to locate storage that requires specific modules. That kind of mismatch can happen after updates or after copying configurations between systems that are similar but not identical. For exam questions, The clue is a system that starts booting but fails during early device discovery or root mounting, especially after changes that affect kernel or boot components. The story you should tell yourself is that the kernel did arrive, but it did not bring the right toolbox to finish preparing the environment. Timing and readiness are another subtle source of boot breakage, especially when storage devices take longer to appear than the boot configuration assumes. The kernel and early user space may start looking for the root file system before a device is fully ready, particularly with certain storage types or complex setups. In a healthy system, the boot process includes mechanisms to wait or retry, but parameters and configuration choices can affect those behaviors. If a configuration is too aggressive about expecting immediate availability, it can create a failure that looks like a missing disk even when the disk is fine. On an exam, you may be given symptoms that resemble missing devices, but with hints that the issue appeared after a change or under certain conditions, and that can point to readiness assumptions rather than actual hardware failure. The key exam insight is that early boot is time-sensitive, and configuration can influence whether the system is patient or impatient. Understanding that prevents you from choosing overly drastic answers like assuming total corruption when the more accurate explanation is a mismatch between expectation and timing. Boot configuration is also where you sometimes see choices that control what happens after the kernel starts, such as which mode the system should reach when it transitions into normal user space. Modern systems often rely on a service manager to bring the system into a desired operational state, and parameters can influence which target state is selected. This matters because a system can boot into a minimal or recovery mode intentionally, and if that becomes the default, it can look like something is broken when it is actually following instructions. For beginners, this is an important concept because it shows that not every unusual boot outcome is a failure. Sometimes it is simply the system doing what it was told. The exam may describe a system that boots but does not start expected services, and your job is to consider whether a boot time setting changed the intended mode. In that situation, answers that focus on reinstalling software are usually too extreme, while answers that focus on correcting the intended startup mode align with safe reasoning. The broader lesson is that boot parameters are levers, and moving a lever changes behavior, sometimes dramatically. When you see the phrase kernel parameters, it is tempting to imagine an endless list you must memorize, but the exam is more approachable when you group parameters by what kind of decision they influence. Some parameters influence identity, like where root lives, which is fundamental. Some influence visibility, like how much you can observe during startup, which affects troubleshooting. Some influence compatibility, like toggling hardware features or selecting a simpler behavior path for debugging. Some influence control flow, like which environment or mode the system should enter after startup. If you think in groups, you can interpret unfamiliar parameter names by asking which group they seem to belong to based on the scenario. That is exactly the kind of reasoning the exam rewards, because it mirrors real-world troubleshooting where you often do not know a detail, but you can still reason from the category. The exam also tends to include distractors that sound technical but do not match the type of failure described. Group-based thinking lets you reject those distractors quickly because you know what kind of lever would produce the symptom. Another major source of breakage is configuration drift, which is when the boot recipe no longer matches the reality of the installed system due to updates, partial changes, or mixing components from different moments in time. Drift can happen if a kernel is updated but the associated early image is not, or if a storage layout changes but the root identifier in the boot recipe stays pointed at the old structure. Drift can also happen if a system has multiple kernel entries and the default selection changes unexpectedly, leading to a boot into a kernel that is not the one you thought you were using. For exam thinking, drift is a powerful concept because it explains why something that used to work can stop working without any dramatic visible damage. The pattern is consistency. Boot works best when the bootloader entry, the kernel, the early image, and the root file system assumptions all align. When they do not, you see failures that are confusing until you remember the boot story and ask which pieces are out of sync. Many exam questions are really drift questions in disguise, and recognizing that can save you time. Finally, it is worth tying boot configuration and kernel parameters back to the exam's decision-making focus, because the test is often trying to see whether you choose the smallest safe change that restores alignment. When a system fails to boot after a configuration change, the safest move is usually to revert or select a known good boot path rather than making a sweeping change that could introduce new problems. When a symptom suggests the kernel cannot find the root file system, the safest reasoning often involves correcting identification and assumptions rather than assuming the entire disk is broken. When the issue looks like a mismatch between the kernel and early environment, the safe logic is to restore a compatible pairing rather than to keep layering troubleshooting flags that reduce functionality. This is not about heroics. It is about controlled recovery and understanding what each knob changes. The more you practice thinking in terms of assumptions and handoffs, the easier it becomes to interpret a boot problem as a predictable result of a specific incorrect instruction. When you can do that, boot questions stop being intimidating because you are no longer guessing in the dark. By the end of this lesson, you should be able to explain boot configuration as the recipe that chooses what starts and what assumptions are handed to the kernel, and you should be able to describe kernel parameters as specific levers that influence early decisions about storage, compatibility, visibility, and startup mode. You should also be able to articulate why boot breaks so easily when those levers are wrong, because early boot depends on correct assumptions and has limited ability to recover if the assumptions are false. The exam will not require you to be a walking encyclopedia of parameter names, but it will reward you for recognizing patterns like mismatched components, unstable storage identifiers, hidden visibility, and drift after changes. If you keep the boot flow story from the previous lesson in mind, these configuration ideas fit naturally into it, because they explain why the bootloader chooses one path and why the kernel behaves the way it does once it is running. Most importantly, you now have a safe, repeatable way to reason through boot-related scenarios. Identify the stage, identify the assumption, and choose the smallest change that restores alignment. That habit is exactly what carries you through time pressure on the exam and through real troubleshooting later.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.